Yeah, so I'm Ahmad from Aragon. I'll be talking about a project joint with Aztec as part of Noun's DAO's private voting research sprint. Um, and we're trying to accomplish private voting. And so a summary is we have a token-based voting system, so one NFT, one vote. We assume we have some kind of DAO. Membership is, I guess, defined by ownership of an NFT. Voter anonymity throughout the process and also after the process. That was one of our goals. We should have shielded votes for the duration of the voting period and on-chain verification. So we're trying to minimize off-chain dependencies as much as possible. So let me just talk about the design from a high level first. So first of all, from the front end perspective, someone acquires an NFT, registers to vote. So the registration, the way we see it, you could either have it be DAO specific or have some kind of central registry. The idea here being tied in with what Piotr was talking about during his talk, where you probably don't want to pass in your SEC P256K1 private key into a snark. You want to use something more snark friendly. In our case, it's Baby Jub Jub. And then voting process is created, people cast their votes, and then at the very end of the voting period, so at the very start of the voting period, I'll talk about this in a moment, we have some kind of public key that comes out of a time-locked service. In our case, we use the League of Entropy. I'm not going to say too much about that because it's a different component of the project, but that is what we use to kind of guarantee that some trusted parties provide us with a public key whose private key will only be revealed at the end of the voting period. So private key revealed, and then anybody can compute the results, publish them, and then some action might be executed on chain, transfer of funds, etc. And from the backend perspective, for each step, so basically vote process creation, voting, and computing and publishing results, you basically run a computation locally. In our case, we provide a CLI. Everything here is open source, by the way. It's on GitHub. Ideally, we do things in the browser, actually, and that's kind of the next step. But you run a computation, generate a certain ZK proof, submit the public inputs and the proof to the contract, which then verifies the proof, and then will either store data or emit it in the form of logs. Yeah. So just a quick refresher, because this is essentially what everything relies on. So the census is basically defined by ownership of an NFT and being registered to vote. So what we need to do is we actually need to use storage proofs, which were also talked about earlier. So it's just a refresher, so a very quick picture of the way things work on Ethereum is you have your blocks, and in each block you have a state root, and then you can trace it down. So it defines the root of a Merkle-Patricia trie. You trace it down to get to a certain account, which then has a so-called storage root in it, which is the root of another trie, which basically has all the storage slots of that contract. In our case, we have two contracts, a registry contract and an NFT contract that have to be traced down to. And then once you're in one of those contracts, you basically trace from the storage root down to the value you actually want to recover from a certain field, from a certain storage slot. In our case, for the registry contract, we want to associate a public key, a Baby Jub Jub public key with an address. And in the NFT contract, you basically want to go from an NFT ID to the same address. So now I'll talk about the implementation in a bit more detail and where the challenges lie. So the assumptions are we have Ethereum blockchain, some fixed NFT contracts, some ZK Snark proving system, underlying fields, FP. For us, this is the BN254 associated field, an embedded curve. In our case, it's the prime order, the canonical prime order subgroup of Baby Jub Jub, and we should have the possibility of on-chain verification. So here we use Ultraplonk via Noir, which readily lends itself to such applications, as we'll discuss in a moment. We assume given some ZK Snark-friendly hash function. I'm kind of half lying here because the hash function is Poseidon, and if you've ever looked under the hood, my Poseidon might not be your Poseidon, might not even be a hash function. And then we assume we have some trade-off hash function, H1, that should be, I guess, cheap enough to do within a snark, but cheap enough to do on-chain. In our case, we just kind of defaulted to Poseidon again, but yeah, you could choose whatever you like, depending on what trade-off you're willing to make. And then we assume we have some time lock service for verifiably random key generation. We essentially want, a public key at the start of a voting period, and then a private key at the end, and some notion of trust so that the private key can never be revealed beforehand. So that's the setup. And the contracts involved, we basically have 3 contracts here. Registry contract, which simply has a one-to-one correspondence, well, not one-to-one, but basically a correspondence from between addresses and public keys. And we assume that you could have different schemes and different types of public keys. We're actually working on a service of our own called ZK Registry that would accommodate for different types of keys. We have the voting contract, which basically contains all the necessary data. So this would be deployed by each DAO. You'd store in it basically the various proposals in the form of process numbers, maybe an IPFS link to the proposal, possible vote choices and actions, voting period, and time lock public key. The results would also be stored, but ballots would be logged, not stored in the contract. And we assume also some verifier smart contracts to verify the various snarks, depending on what proving system you use. And so for voter registration, which goes via that registry contract, you basically do the following, and we actually have a browser implementation of this. You connect your wallet via MetaMask. You generate some private key by signing a certain message. Again, this is going back to that first talk. It's exactly the same idea. And then you compute the corresponding public key, and then you submit that to the smart contract. And you do this from your own address. So you might think maybe this breaks anonymity. But I mean, if you're in a DAO, chances are, you'd want to register to vote. So everyone in the DAO should really register to vote. That's kind of like the underlying assumption here. Voting process creation. So this is where things start to get a bit tricky. So the person who wants to create a voting process would ask for such a public key from this time lock service. And besides that, what we essentially want to do is say, okay, at the moment of voting process creation, everyone who's registered to vote, everyone who has an NFT should be eligible to vote. So what we need here are the storage roots of those 2 smart contracts. And here's the catch. You can't get those from within the EVM. That's not possible. What you can get is you can get the block hash corresponding to a certain block number. So what you do is you say, hey, we're at block number N. And then you fetch all the necessary data via eth_get_proof, which was mentioned in the last talk. And you can do that for the past M blocks, where M is not a particularly large number. And that's not really a big deal here. Will be a big deal in a second. You fetch all that stuff. And then what you do is you put together a succinct proof. You could submit this all to the smart contract, but then you need to measure the costs. But you could put together a succinct proof that the block hash is actually consistent with the state root that you will submit to the smart contract. And you would do that by just check hashing, which we can do. But then you need to actually trace down the trie, provide a trie proof that these storage roots actually correspond to the state root you're submitting. And so already we're seeing some trie proofs happening. And for voting, so part of this is, I think, fairly straightforward. You basically sign a couple of messages, basically involving your NFT ID, the voting process ID, which also contains information like chain ID, for example, so that you can't get replay attacks happening. You sign your ballot, essentially. You compute a nullifier, you submit that, and then you generate a random private key for your vote. And from that private key and the time lock public key, you compute a shared secret, and you use that to encrypt your ballot, and you submit that. Now, this private key should be thrown away, else you're in trouble. But you never submit it. You only submit the public key, because later on you'll be able to brute force the vote out of this encrypted, sort of shared secret encrypted ballot. And you have to obtain storage proofs, basically guaranteeing that your address A corresponds to the public key Z that's in the registry, and that the NFT with NFT ID NFT is owned by you. And you generate a ZK proof verifying all the above. So basically, we use EDDSA here for the signatures, by the way. So for our particular implementation, so we would want something like that. You basically verify the signatures, verify that this is all correct, submit that as a ZK proof, and you're good to go if everything lines up. And then for tallying, so computing the results, in the end, you're going to have that private key. So you can easily decrypt the ballots by computing that shared secret, which you can now do because you have the other private key, but you have the public key of the randomly generated key that's been thrown away, hopefully. You can compute the results of the voting process. And as the votes come in, there's actually, not sure if I mentioned that way back. If we go back to the, let's see, where was it? You're not quite sure where I mentioned it. Should have mentioned it. But essentially, as the votes come in, we actually hash up these Bs over here. So these encrypted votes. So we basically start from 0, and then using this trade-off hash function, as we get a vote in, so in our case, it's Poseidon on 2 elements, the Poseidon permutation, then projected onto the first component. So as you get in ballots, you basically take the aggregate that you have so far, which starts at 0. You tack on the encrypted vote or encrypted ballot that's come in, and then you hash that, and you keep doing that as they come in. So as you actually compute the results, you're going to have to compute that as well, and that has to match up with what's in the smart contract. So you submit all of that, and if all is well, then yeah, you've published the results, and whatever action needs to be undertaken can be undertaken. So there are some challenges and drawbacks. So if you go back to the vote submission, you actually need storage proofs in there. Now, if your voting period's like an hour long, not a problem. Pretty much every node, every Geth node, which would be all nodes that are widely used. So much for decentralization. In general, you'd want an archive node. So we're in luck because Infura is there, the one. Tri-proofs are very expensive in a ZK snark. So essentially, with this collaboration with Aztec, we've kind of gone back and forth about what exactly we need to do inside the circuit. And there are lots of Ketchak hashes that need to be computed. Everything in the trie is RLP encoded. So you basically have to decode all these bytes. And it's not a very natural thing to do in a snark. P-lookups really help in dropping the constraint count. So we're at something like, I think it was a few 100,000 constraints. So about 700,000 constraints for a depth 8 proof. Which is pretty good. So there are implementations in CIRCOM and Halo 2, and the CIRCOM numbers are quite a bit bigger than that. And also, things being expensive in a snark contributes to proving time cost. So it takes a few minutes to create a voting process and to vote. I think it was something like 7 to 12 minutes on my laptop. So this is getting better and better. At the moment, it also takes around, or it I think it takes 8 minutes to compute a tally for about 256 voters, but multi-threaded proving is coming to Noir, for example, so that should bring the time down considerably. And the other thing to keep in mind is we can't exactly save the whales. So it's one NFT, one vote. So per NFT, you submit a single vote, and that is going to cost a lot. So gas costs are quite high. So we're talking a few $100K for pretty much each step. And that most of that is in the verifier smart contract cost. So there are ways around this, like having a delay relayer, or the other thing is you could correlate the whales, right, to the votes. Then you might want delegation to get around that. That's another way to sort of tackle that. And delegation is something that we've implemented for certain, I guess, extended NFT contracts, as the Nouns DAO contract, for example. So our outlook is basically to move everything to the browser. We'd have to make use of recursive proofs for this because memory limitations. And Noir does have some, or will have some support for recursive proofs. As I said, some kind of delay relayer to get around correlations, further optimization, and DAO integration. I mean, you would want so at Aragon we have this framework for putting DAOs together without code, and it would be nice to kind of hook into that, not just have everybody use the CLI because it seems not everyone's keen on the CLI. So yeah, that's pretty much all I wanted to talk about. And yeah, everything is on research.aragon.org. We have blog posts. All our code is on GitHub, the canonical Git server. And yeah, that's it for my talk. Thank you for your attention. Thank you for giving me the opportunity to speak.